Hello, welcome to my channel. In this video, we are going to be taking a look at the molar heat capacity for an algae gas. And the first thing we need to consider is the first law of thermodynamics, which is giving us Q equal to change in U plus W, where our Q is the amount of heat that is supplied to the system or taken out of the system. Our change in U is the internal energy, while W is the work done. Our change in U here depends on temperature, especially for an ideal gas. And the reason why we have change in U is because when there is a temperature change, right, our system can move from one state to another state. So we have a change in U. This equation here can be re-expressed as Q equal to change in U plus PdV, where this one is the pressure and change in volume. Remember, this is our work done. Now, it's important for us to take note of some of the processes involved in thermodynamics, and one of them is the adiabatic process. And for the adiabatic process, it tells us that the Q, the amount of heat transferred into the system, is zero, or no heat is transferred into the system, or heat is taken out of the system. And once it is zero, we are left with change in U, which is the internal energy, is equal to minus W, because then this one will be zero. So we have Q equal to zero, change in U equal to minus W. The second process is the isochoric process. And for that, we are considering constant volume. And if you check this same equation, at constant volume, everything will become zero. We have Q equal to change in U. So we have our work done will be zero. Q will be equal to change in internal energy. Then the third kind of process is the isobaric process. And that tells us that the pressure in that system is constant. And when it is constant, take note of this equation. If pressure is constant, then nothing will happen. This equation will remain the same. So we have this expression. Then finally, we have the isothermal process. And that tells us that the temperature for that system is constant. And when it is constant, recall that we said the internal energy is dependent on temperature, especially for an ideal gas. So if it depends on temperature, so we can as well guess that this one will be equal to zero. So our Q will be equal to work done, right? So we have Q equal to W. Now at this point, it's important for us to take a look at the molar heat capacities of gases. Now, recall that from our previous knowledge of specific heat capacity, that the amount of heat given into transferred into a system is equal to mc dt, where our m is the mass of the substance or the system that we are studying, c is the specific heat capacity, then this one is the change in temperature. This particular equation is very, very useful when we study solids and liquids. But when we study gases, it's no longer useful. So we want to find another an equation that can be used to describe gases in a system. So what we'll do is to consider this expression where we have the mass equal to number of moles times the molar mass. So wherever we see our mass, we replace with Nm in this equation. So we have dq equal to Nmc dt. At this point, our mc can be replaced with a single parameter, and we call it dq equal to n, which is number of moles, c subscript x dt, where our x here can take the value of p, which stands for pressure, or v, which stands for volume. Now remember, our cx is the molar mass times the specific heat capacity. I hope that's good. So we'll move on to the next phase. Let's see the connection between the Cp, which is the molar heat capacity at constant pressure, and molar heat capacity at constant volume. And for us to deal with this, let's recall our first equation for first law of thermodynamics, which is giving us this. So let's consider a scenario where we have a container, a rigid container that is filled with gas, and we supply heat to the system. Now, as long as the body, the system, the container is rigid, it means that there will be no change in volume. At that point, this one becomes zero. the work done is 0. So we have dV equal to 0, so dQ equal to change in internal energy. At this point, if we go back to the formula for molar heat capacity, we expect that as long as the volume is not changing, then this will be the amount of heat that is supplied to the system at constant volume. Now at this point, we can see that dQ here is exactly equal to dQ here. And what does that imply? It means that our change in internal energy must be equal to this part. So we have the change in U equal to NCV dt. Now let's now consider another scenario at constant pressure, how to calculate the molar heat capacity at constant pressure. So imagine a container, right, filled with gases, and you supply heat to the system. Definitely at the point we know the pressure will likely to increase. So, but if the volume is adjusted in such a way that the pressure remains constant, then what will now happen is that this equation will remain the same. So at this point, the volume changes to accommodate for constant pressure, right? And when we now bring in our Q, the amount of heat supplied to the system, we have the Q equal to N molar heat capacity at constant pressure times dt. So at this point, we can now compare this equation with this. And we see that dq here is dq. So everything here will be equal to everything here. And that gives us ncp dt, which is this part, is equal to this internal energy, which has been found to be ncv dt plus p dv. At this point, let's see what we can do to manipulate this p dv. Recall from our equation of state for an ideal gas, which is giving us PV equal to nRT. We can differentiate this one to have PdV plus VdP equal to nRT. These two are constants. They are not changing. Now, because we are considering constant pressure, which supersedes all this one as constant pressure, right? This part will be 0 because there is no change in pressure. We are left with PdV equal to nRT. So since PdV is here, we just replace PdV with nRT and we have this expression. So what you notice is that n dt is common throughout. So they will take care of each other and we are left with Cp, molar heat capacity at constant pressure, is equal to molar heat capacity at constant volume is equal plus our gas constants. So from this point, we can see that the molar heat capacity at constant pressure is greater than that of the molar heat capacity at constant volume. Okay, so at this point, let's consider another situation where we have an adiabatic process. Now, recall that this expression for an adiabatic process, the Q is 0 because no heat is transferred into the system or heat is taken out of the system. So if that's the case, we are left with dQ equal to 0, du equal to minus W or minus PdV. But we also notice that our P from here, we can make it the Soviet formula and replace with nRT all over V and substitute here. So that our change in U, which has been found to be NCV dt, is now here equal to P here is now nRT all over V dV. At this point, N can take care of N and rearrange. We have dt all over T, that is, this T comes down here, then dV all over V, then R all over CV from this point. Okay, now that we have established that R, from here we can replace R with Cp minus Cv. That gives us dt all over this with this expression. Okay, so we can take this one to this bottom, take this one to this bottom, so that it becomes Cp all over Cv minus 1. And that gives us this expression. So we can redefine this ratio as a new parameter called gamma. So we call it gamma minus 1. So whenever we see gamma, it is Cp all over Cv. Everything here can come back and we have this expression equal to 0. At this point, if we integrate both sides, that's this part and this part, we have ln T, ln V equal to constants. And that gives us this expression. From our law of indices, we can take this one to this part, right? And that gives us ln T plus ln V gamma minus 1 equal to constants. And we can combine these two because they are both lane to give us lane TV gamma minus 1 equal to constants. Now, making TV the separate formula, lane will come here, becomes exponential. Everything there will still be constant. And we have TV raised by gamma minus 1 equals to constants. So that's it for this particular one, right? So let's also consider for the fact that as long as this one is a constant, it means that T1, which is the temperature at the first state, times V1, which is the volume at that first state, must be equal to T1 V1. So we have something of this form as long as this one is a constant, right? Okay, so let's see if we can replace our T with a new parameter, which is the pressure. And first of all, we recall that our T equal to PV all over NR. So wherever we see T, we replace with PV all over NR. So bring it here, P1 V1. Remember, all over NR will appear here. All over NR will also appear here, and they will both cancel out. So V1 multiplies this will result to V raised by gamma. So finally, we have P1 V1 raised by gamma equal to P2 V2 raised by gamma. So at this point, if we combine these two equations, therefore we can say that this equation and this other equation holds only for ideal gas and adiabatic process. So when we're considering an ideal gas situation, right, or an ideal gas for an adiabatic process, this equation holds, right? So let's still continue. For an adiabatic process, other formulas that can be generated from this same process. So recall that we have our change in U equal to minus N CV dt equal to work done. We might want to find out the work done on that system when the system undergoes an adiabatic process. So remember, our dt here is nothing but T2 minus T1. And that gives us minus NCV T2 minus T1. If N minus goes inside, it becomes NCV T1 minus T2. So this is the work done for that system. We can also rearrange it in such a way that our PV all over R equal to NT, right? So wherever we see our T, we can also replace with PV, P1V, because our T here and N, they go together. So we have P1 V1 minus P2 V2 all over R. And that's it. I hope this helps. Please like, share, and subscribe. Thank you.